All right, so what we're going to be doing today is learning how to find the zeros of polynomials. And we're going to be doing this using a method called synthetic division. And synthetic division is pretty much like the basis for this entire unit. Like, it's a very important concept, but honestly, it's not bad. But the way we're going to find the zeros of these polynomials is by using a technique or a theorem called the rational zero theorem, which I put right there. Um, so the rational zero theorem states that if f of x is a polynomial with integer coefficients and p over q is a zero of that polynomial, then p is a factor of the constant and q is a factor of the lead coefficient. So I will show you what this means in just a second. So like polynomials, we have seen quadratic. We've seen like x to the squared plus something else. We have not seen like x to the third or x to the fourth or x to the fifth. I think in this unit there might even be some x to the seventh or x to the sixth. Like we are going to be figuring out how to solve these, how to work with these larger degreed polynomials. And the way we're going to find these roots or these zeros of these larger degree polynomials is using the rational zero theorem. So the first thing we have to do here is figure out our polynomial. So the example polynomial we're going to be using is this one right here. So let's see, we got 2x, or f of x equals, f of x equals 2x to the fourth plus x to the third minus 19x squared minus 9x plus 9. And we are going to be using this polynomial and finding the rational zeros of it. So the first thing we want to do, well, because it is a degree 4 polynomial, the highest degree on any variable is a 4. That means there are 4 answers I'm looking for, 4 zeros, 4 solutions. Actually, yeah, I'll call them zeros because they're zeros, not solutions. We're not solving anything. So there are 4 zeros we're looking for in this polynomial. And now let's break down the rational zero theorem. It says I have my polynomial f of x. Yeah, I do. With integer coefficients. It does have integer coefficients because it has 2, 1 x to the third, negative 19x squared, negative 9x, and 9. P over q is the zero of that polynomial. Well, I don't know what the zeros are yet, but I'll take their word for it. And p is a factor of the constant, and q is a factor of the lead coefficient. So first, let's identify the constant and the lead coefficient. The constant is this number here on the end, this 9, that doesn't have any variables attached to it. So the constant here is going to be 9. And the lead coefficient is this number on the very front next to the x with the highest exponent. So my lead coefficient is this 2. So we'll call that LC. So now let's break down that rational zero theorem just a little bit more. And again, we are looking for 4 zeros. So let me just go right here. So it says p is a factor of the constant. So let me list my possible p-values. Well, my constant here is 9, which means the first factor of 9 is positive or negative 1, because I can divide 9 by 1. And the next thing that I can divide 9 by is going to be 3, because it wouldn't be 2, because I can divide 9 by 2. And the final thing is going to be 9. My q values, the factors of the lead coefficient. Since my lead coefficient is pretty easy, it's just 2, that means I only have 2 q values. I have positive or negative 1 and positive or negative 2. So there we go. Now I want to take p over q, because p over q is going to be my zeros of the polynomial. I know, or I don't know what my zeros are yet, but I know that whatever they are, that they have the form P over Q. So first thing I need to do, or the next thing I need to do, is list my possible rational zeros, so I know what I'm testing here. So I'm going to take one number from the P and one number from the Q. So if I take 1 from P and 1 from Q, that's just 1 over 1. So that means that my first possible rational zero should be positive or negative 1. So yeah, I'm taking P over Q because I took the 1 from P, the 1 from Q, yeah, positive or negative 1, sorry. And now I'm going to take the 3 from the P and the 1 from the Q. So 3 over 1, that's going to give me 3. Next thing, I'll take the 9 from P and the 1 from Q. So that gives me positive or negative 9. However, I still have some more I have to do also, because I could have the 1 from the P and the 2 from the Q, which means I'm going to have positive or negative 1 half because it's P over Q. Or it could be positive or negative 3 halves, or even positive or negative 9 halves, which means that I have this list here of possible rational zeros. So I could have 6 possible rational zeros, or not 6 really, because 12, because it's positive or negative for all of them. So that means there are 6 possible rational, or 12 possible rational zeros that I'm going to need to test to see if they are these zeros. This does not mean that all 12 of these numbers are going to be zeros of this polynomial. It means that 4 of these numbers are going to be zeros of the polynomial. And it's 4 because I figured out that there were 4 zeros earlier. So 4 of these 12 are the zeros of this polynomial. I don't know which 4 yet, but I know that whatever the zeros of this polynomial are, they're on this list. I just listed them somewhere. So I will find the, or I'm going to do some synthetic division to show you which of these zeros it is, or to figure out which of the zeros it is. And synthetic division, it is, in my opinion, a pretty easy thing. It's not hard. So yeah, it's a lot of work. I know it is a lot of work. And not the most fun, but it's easy. So you should be able to get the hang of it, and I'll write synthetic division right here, because it is a big part of the unit, and I'll even highlight that since it's important. So synthetic division. And the first thing with synthetic division, well, if I go back up to my list of possible rational zeros, looking at that, sorry. Oh, I'm going to rewrite my polynomial first. So I have 2x to the fourth plus x to the third minus 19x squared minus 9x plus 9. And then I'm going to go down a little bit. And my first number on the possible rational zeros was positive or negative 1. We can only test one at a time, so I'm just going to go positive 1 as my first number that I'm testing using synthetic division. So what I'm going to do is I'm going to take that number 1 and I'm going to put it in a box, and then I'm going to use the coefficients from that polynomial that I just wrote there, and I'm going to write them next to the box. So I have 2x to the fourth plus 1x to the third minus 19x x squared minus 9x plus 9. And now that I have those coefficients written out, I'm going to give them a line underneath them. So not like directly underneath them, I need to give myself some space because I'm going to be writing things between that line and the coefficients. I'm going to make my box bigger here. I'm going to, the first thing you want to do with any synthetic division is bring down the first number. So this first number, this 2, I'm going to bring that down. And I'll just write that down here, 2. So then I'm going to take the 1 inside the box there, and I'm going to multiply it times the 2 that I wrote down there below that bar. I'll even color it. So I'm taking the 1 and I'm multiplying it times this 2. So 1 times 2, well, that gives me positive 2. And now I'm going to do 1 plus 2 because I have a 1 up there. And I'm adding 1 plus 2. That equals 3. So now I have the 1 inside the box, and I'm multiplying it times this new number, this 3. So I'll color that red. So the 1 times 3 is 3. And now I have negative 19 plus 3. Negative 19 plus 3 is going to be, let me make that black, my bad. Okay, negative 19 plus 3 is negative 16. So now I have 1 times that new number, that negative 16, is going to be, I'll make it purple. So 1 times negative 16 will be negative 16. And if I do negative 9 minus 16, that's going to give me negative 25. And now I'm going to do 1 times negative 25. And 1 times negative 25, that's just negative 25. So 9 minus 25 is going to get me negative 16. And this number here, this negative 16, is the most important number from the synthetic division because, well, okay. So if the last number, that negative 16 we got there, is 0, so if that last number had been a 0 instead of a negative 16, then the number I was testing, so the number I was testing here was 1, is a 0 of the polynomial. So that means if that negative 16 had been a 0 instead, that means 1 would have been one of the 4 zeros of this polynomial. But unfortunately it wasn't, so I'm going to say 1 is not a 0. And I'll even go ahead and highlight that. All right, so the next thing I want to do is go back to my list of possible rational zeros because I tested positive 1, it didn't work. The next thing is going to be negative 1 because we had positive or negative 1. So the next thing I'm going to do is test negative 1. So I'm going to do the exact same thing I did with positive 1. I'm going to take negative 1, write it inside a box up there, and then I'm going to write out my coefficients. They're going to be the same ones, 2, 1, negative 19, negative 9, and 9. Yeah, I'll even highlight those because I got those coefficients from right here. 2 comes from the number in front, the next number well, it's just 1 x to the third. Then I have the minus 19 x squared minus 9 plus 9, which is where the 2, 1, negative 19, negative 9, and 9 came from. But anyways, next thing I want to do with synthetic division is give myself that underline. And I bring down the first number. So I bring down the 2, and negative 1 times 2 is going to be negative 2, and 1 minus 2 is going to be negative 1. So now I have the negative 1 inside the box times negative 1 is positive 1, and negative 19 plus 1 is going to give me negative 18. So negative 1 inside the box times negative 18 is positive 18, and negative 9 plus 18 is 9. Now I have the negative 1 times 9 is going to be negative 9, and then I have 9 minus 9 is 0. And just like I said earlier, if that last number is 0, that means that the number I'm testing is a 0, so negative 1 is a 0 of this polynomial. Because the last number I got there, that most important number, is a 0. So now, I could continue doing my synthetic division with the same numbers, the 2, the 1, the negative 19, the negative 9, and the 9. But I'm not going to, because I had my original polynomial, and I figured out what would happen if I pulled negative 1 out, if I pulled the root of negative 1 out. So now, instead of using this, these 2, this 1, this negative 19, this negative 9, this 9, I'm going to be using these new numbers here, this 2, the negative 1, the negative 18, and the 9. And I'm going to rewrite these into a new polynomial. And instead, I'm going to find the zeros of this new polynomial. So since I'm still looking for 3 zeros, because we said there were 4, I found one of them, I'm still looking for 3, this is going to be 2x to the third. And then I have minus 1x squared. Then I have minus 18x and plus 9. And instead of finding the zeros of the previous polynomial, I'm going to do this one because it has less numbers and it's just going to be easier to work with. I can only do this once I get 0 as that last number there. So I now have 2, negative 1, negative 18, and 9. And so this is what the polynomial would have looked like if negative 1 hadn't been a 0. So the first thing I have to do is actually I have to test negative 1 again. And the reason for that is because I don't, even though I already showed that negative 1 is a 0, it could be a double 0. It could occur twice. It could occur 3 times. It could occur all 4 times. Maybe all 4 of my zeros for this polynomial are negative 1. I don't know, but I'm going to test negative 1 in my new polynomial. So I give myself that underline, and I bring down the 2. So I bring down that 2. Then I have the negative 1 inside the box times the 2 there is going to be negative 2. So negative 1 minus 2 is negative 3. And then I have the negative 1 in the box times negative 3 is going to be positive 3. And I have negative 18 plus 3. That's going to give me negative 15. Negative 1 inside the box times negative 15 That's going to give me 15, positive 15, and 9 plus 15 is 24. So unfortunately, this means that even though negative 1 was a 0, negative 1 is not a double zero. So the next thing I got to do, my possible rational zeros, I had positive or negative 1, and the next number I needed to test was 3. So I'm going to be testing 3. Oh, by the way, the reason that I didn't have to test 1 again is because I already knew that 1 was not a factor or was not a 0 of the first polynomial. So if it's not a factor if it's not a 0 of the first polynomial, it's not going to be a 0 of the second polynomial either. So I'm not going to keep going, or I'm not going to go back to numbers that I haven't tested. I'm just going to, or that I've already tested. I'm just going to keep going to numbers that I haven't tested yet. So yeah, my next number that I haven't tested is 3, and I set it up here. I write my coefficients, and the first thing I got to do, bring down that first number, that 2. So let's see, the 3 inside the box times the 2 that I just brought down is positive 6, and negative 1 plus 6 is going to give me 5. And then I have the 3 inside the box times 5 is positive 15. And the negative 18 plus 5 is negative 3, or plus 15 is negative 3. And the 3 inside the box times negative 3 is negative 9. 9 minus 9 is 0. So, there we go. We got 0 again as that last number, which means 3 is a 0 of this polynomial. And at the beginning we said we were looking for 4, and we found 2 of them. We found negative 1 and we found 3. There are 2 more. And I'll highlight this as well. So I figured out that 3 is a 0. I also figured out that negative 1 is a 0, and there are 2 more. So now I'm going to do the same thing that I just did, where I took those new numbers and rewrote them into a new polynomial. So since I'm looking for 2 more zeros, I'm going to have 2x squared. And then plus 5x minus 3. And I could solve this using synthetic division. But if you look at that, that is a just a quadratic. So I can solve this by factoring also. And honestly, since I can solve it by factoring, I'm going to solve it by factoring. We know how to factor quadratics. That's been like the past 2 units. So I can just factor this instead of solving those solving this using synthetic division. And I know that it's going to have rational roots because I'm looking for the rational zeros here. So that means it can be solved by factoring or the quadratic formula. So I want 2 numbers that are going to multiply to negative 6 because 2 times negative 3 is negative 6. And the number in the middle, my b value, is 5. And I believe 2 numbers that multiply to be negative 6, add to be 5. That is going to be 6 and negative 1. So 2x squared plus 6x minus 1x minus 3 is my quadratic that I'm going to group. Between 2x squared and 6x, I'm going to pull out the GCF. So the GCF of those two is going to be 2x, and once I pull that out, I'm left with x plus 3. And between negative x and negative 3, my GCF is going to be negative 1. And once I plot -1, I'm left with x plus 3, which means my two factors of this are 2x minus 1 and x plus 3. And since I'm looking for the zeros of this polynomial, I have to set this equal to 0. And to solve this, that just means I have to set each factor separately equal to 0. So I have 2x minus 1 equals 0, and I have x plus 3 equals 0. So if x plus 3 equals 0, I can just subtract 3 from both sides, and I get x equals -3. If 2x minus 1 equals 0, well, I can start by adding 1 to both sides. So 2x equals 1. Divide by 2 to get x equals 1/2. And now I just solved that x equals 1/2 and x equals -3. And I had already solved two zeros because I had -1 and 3. And if I look at my possible rational zeros, all 4 of those numbers are going to be on my list. I had -1, I had +3, I had -3, and I had +1/2. So I listed my possible rational zeros, and even though all 12 of those weren't, the 4 that were the actual rational zeros were on that list. So there we go. -1, +3, -3, and 1/2. It could have been 9, it could have been -3/2, it could have been +9/2, and it could have been +1, but it wasn't because it was these 4 that I just solved, and I solved using synthetic division. So what this means is that, well, originally we were looking for 4 zeros, and we found the 4. So the zeros, yeah, I'll write this a little smaller. So the zeros of the polynomial (2x to the 4th minus or plus x cubed minus 19x squared minus 9x plus 9 are, we said they were -1, 3, -3, and 1/2. So there we go. We got our 4 zeros, and we knew there were 4 because it was a 4th degree polynomial. And there are the 4 zeros. All right, so let's try another example of this. And this one is going to have some bigger numbers in it, but it's still doable. So this example, we will do, hold on, let me pull it up. Okay, so we got f of x equals 3x to the 5th minus 32x to the 4th plus 118x to the 3rd minus 164x squared plus 39x plus 36. All right, so that 36, that's my constant. First thing I want to do is mark the constant and the lead coefficient. Dang it. Constant. And then the 3 out front, that's my lead coefficient. And because of that 5 next to the lead coefficient, I know I'm looking for 5 zeros. There are 5 solutions. This is x to the 5th, so there are 5 solutions to this polynomial. So first thing I want to do is list my p-values. My p-values, those are going to be the factors of the constant, the factors of 36. So I got positive negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, positive negative 9, positive negative 12, positive negative 18, and positive or negative 36. So there's 9 different possible values of p. And fortunately, q is going to be a lot simpler because my lead coefficient is just 3, and the factors of 3 are 1 and 3. All right, so I want to list my possible rational zeros. And those are going to be the p-values over the q-values, just like they were last time. So I'll start by just doing the q in the denominator is going to be 1. So I can just go with all my p-values. So positive negative 1, positive negative 2, positive negative 3, because 1 over 1 is 1, 2 over 2 is 2, 3 over 1 is 3, 4 over 1 is 4, 6 over 1 is 6, 9 over 1 is 9, 12 over 1 is 12, 18 over 1 is 18, and 36 over 1 is 36. Next, I have my other q value could be 3. So I need to do the 1 in the p divided by the 3 in the q. So that's going to give me positive or negative 1/3. Next, I have positive or negative 2/3 because 2 in the p divided by 3 in the q. But then I have 3 in the p over 3 in the q, or 3 over 3, that's just 1, and 1 is already in my list, so I don't need to repeat that. So the next number, I have 4 over 3, I do need to list that one because that one's new, 4/3. But then I have 6 over 3, 6 over 3 is already there, it's 2. 9 over 3, 9 over 3 is 3, that's just already on my list. 12 over 3 is 4, which is already on my list. 18 over 3 is 6, which is already on the list. And 36 over 3 is 12, which is already on the list. Which means that the possible rational, the only new numbers I added were those 3 fractions on the end. So the possible rational zeros of this big polynomial are 1, 2, 3, 4, 6, 9, 12, 18, 36, 1/3, 2/3, and 4/3. And just like the last time, just because they are listed here does not mean that they are a 0. And I know that I do have that my zeros are going to be somewhere on this list, and there's 5 of them, and all 5 are in here somewhere. So the first thing I'll do is my synthetic division. By testing 1, I write out my coefficients. So I have 3, negative 32, 118, negative 164, 39, and 36. And I'm testing 1, I'm testing positive 1 because it's the first number on my list of possible rational zeros. So first thing I do is bring down that 3, and then I do the 1 inside the box times the 3 there. It's going to give me positive 3. And I have negative 32 plus 3 is negative 29. The 1 inside the box times negative 29 is negative 29. 118 minus 29 is, I believe that's 89. Yeah, 89. So I have the negative 1 inside, or I have the 1 inside the box times 89. It's going to be positive 89. So negative 164 plus 89 is going to give me negative 75. And the 1 times the negative 75 is going to give me negative 75. 39 minus 75, that is negative 36. And 1 times negative 36 is negative 36. 36 minus 36 is, fortunately, 0. So we were looking for 5 zeros, and since we got 0 at the very end, we know that our first 0 is 1. So 1 is a 0 of this polynomial. I'll highlight that. All right, so now I'm going to make a new polynomial that has these coefficients. Instead of those big numbers like the 118, the negative 164, I know that like 89 and negative 75 are still big numbers, but not as big. So since I'm looking, I found 1 0, and I'm still looking for 4 more because it was fifth degree, which means I have 3x to the fourth minus 29x to the third plus 89x squared minus 75x minus 36. This is my new polynomial, and these coefficients are the ones that I'm going to be using to test the synthetic division for my next part. So let's see. I do need to test 1 again to see if it's a double 0. So first thing I will do is okay, so I'm just going to be doing synthetic division again, just with this 1. So my new coefficients are 3, negative 29, 89, negative 75, and negative 36. And give myself that nice underline, bring down the first number. So I'm going to write my 3 down there. And the 1 inside the box times 3 is going to be positive 3. So negative 29 plus 3 is going to be negative 26. 1 in the box times negative 26 is negative 26. See, 89 minus 26 is going to be 63. So 1 times 63 is 63. Positive 63. Negative 75 plus 63 is negative 12. 1 times negative 12 is going to give me negative 12. Negative 36 minus 12 is negative 48. And unfortunately, negative 48 is not 0, which means that even though 1 was a 0, 1 is not a double 0. All right, perfect. So the next number that I needed to test my possible rational zeros, looks like it was negative 1. Yeah, so I'll go down here. So I just need to keep going because I still need 4 more zeros. I got one of them. The others are out there somewhere. So I'll test negative 1, put it in inside my box. And let's see, what were the coefficients? It was 3. So yeah, 3, negative 29, 89, negative 75, and negative 36. And I'll give it that underline. And first thing I do, bring down the 3. So now I have the negative 1 inside the box times 3 is negative 3. Negative 29 minus 3 is negative 32. Negative 1 times negative 32 is positive 32. So 89 plus 32 is going to be 121, yeah. And negative 1 times 121 is negative 121. And negative 75 minus 121, that's going to be negative 196. And negative 1 times negative 196 is going to be positive 196. And negative 36 plus 196 is 160. So very clearly, that last number there, that 160, that is not 0, which means negative 1 is not a 0 of this polynomial. So even if we do get these big numbers like this negative 196 and this 160 and this 121, like even if you find yourself getting those, like there's a chance you did something wrong, but sometimes when you do synthetic division, you're just going to get some big numbers, and that's okay. As long as you either prove or disprove something and then can reuse those big numbers. So maybe our new polynomial would have had negative 196 in it. We don't know. Anyways, the next number I need to test from my list of possible rational zeros was positive 2. So I'm putting positive 2 in the box, and I'm listing out my coefficients again. I give them an underline, bring down the 3, and the 2 in the box times 3 is 6, positive 6. Negative 29 plus 6 is negative 23. 2 times negative 23 is negative 46. 89 minus 46 is going to be 43. 2 times 43, that's going to give me positive 86. Negative 75 plus 86 is 11. And 2 times 11 is 22, positive 22. So negative 36 plus 22 is unfortunately negative 14. So even though it was closer to 0, a lot closer to 0 than the last one was, it's still not 0. So this means 2 is not a 0 of the polynomial. All right, so we did 2. Keep going. We've got to do negative 2 now. All right, so list out the coefficients. 3, negative 29, 89, negative 75, and negative 36. So bring down the 3. So I got 3 times negative 2 is negative 6. Negative 29 minus 6 is negative 35. Negative 2 times negative 35 is positive 70. 89 plus 70 is 159. Negative 2 times 159. Gotta get out my calculator for this one. So negative 2 times 159 is going to be negative 318. Negative 75 minus 318 is going to be negative 393. And negative 2 times negative 393 is going to be positive 786. Negative 36 plus 786 is 750. And very clearly, 750 is not 0, which means negative 2, there's no way that's a 0. So negative 2 is not a 0. All right, keep going on the list. I think the next number was positive 3. We'll go check that. Yeah, our possible rational zeros, we did negative or positive -1, positive -2. Next we got positive 3. So put the 3 in the box and list our coefficients. We got 3, we had -29, we had 89, we had -75, and we had -36. Bring down the 3, give it that underline. So I have the 3 in the box times 3 is positive 9. -29 plus 9 is -20. 3 in the box times -20 is -60. 89 minus 60 is 29. 3 times 29 is going to be 87. Yeah, 87. Positive 87. So -75 plus 87 gives me 12. And 3 times 12 is positive 36. -36 plus 36 is 0. So luckily, we were looking for those 4 more zeros. We found another one. One of them is 3. 3 is a 0 of this polynomial. Because I got 0 there on the end. All right, so now I'm going to take these numbers and change them into my new updated polynomial. So instead of 3, -29, 89, -75, and 36, I'm going to have 3x to the third, because I'm looking for 3 more zeros, minus 20x squared plus 29x plus 12. And I'm going to be finding the zeros of this new polynomial here. 3x to the third minus 20x squared plus 29x plus 12. And I did test if 3 was a 0, but I didn't test if it was a double 0, so I do have to test 3 yet again. So I put 3 inside the box, and then my new coefficients are going to be 3, -20, 29, and 12. I give them an underline, and let's see, so bring down the 3. 3 times 3 is going to be positive 9. -20 plus 9 is -11. 3 in the box times -11 is -33. 29 minus 33 is going to give me -4. And the 3 in the box times -4 is -12. 12 minus 12 is 0. So even though 3 was a 0, 3 is also a double 0, which means of the 5 zeros that there were in this polynomial, at least 2 of them were 3. You know, I do have this new polynomial now, and maybe 3 is another 0. So 3 could be a double 0, it could be a triple 0, it could be a quadruple 0. Maybe all 5 of my zeros for this polynomial are 3. That's a possibility. But using these new coefficients, I'm going to write a new polynomial, or actually, in this case, it's going to be a quadratic, because I have 3x squared minus 11x minus 4, because I'm looking for 2 more zeros. So just as before, we are left with a quadratic. And I could continue if I wanted. I could continue with the synthetic division, but I'm just going to factor this like I factor quadratic. I want 2 things that are going to multiply to be -12 and add to be -11. And those 2 numbers are going to be -12 and 1. So 3x squared minus 12x plus x minus 4 I'm going to factor out the GCF. So between 3x squared and negative 12x, I can pull out a 3x, and I'm left with x minus 4. And between x plus 4, I can't pull out anything, so I'm going to pull out a 1 because there's no common factor there, but I still have to pull out something. So that gives me 3x plus 1 times x minus 4 equals 0, just like before. So I have to set each factor equal to 0. So 3x plus 1 equals 0, and x minus 4 equals 0. Well, if x minus 4 equals 0, I can just add 4 to both sides, and I get x equals 4. If 3x plus 1 equals 0, I can subtract 1 from both sides, so I'll have 3x equals negative 1, and then divide by 3, x equals negative 1/3. Which means my remaining two zeros that I was looking for are going to be negative 1/3 and 4. And I already solved 3 of the zeros for this polynomial. The last two are going to be negative 1/3 and 4. So let me go all the way back up to my list of possible rational zeros, and I found that the zeros of this polynomial were once again on here. I had positive 1, I had positive 3 twice, I had positive 4, and over here I had negative 1/3. So again, even though there was this long list of possible rational zeros, all the zeros that it could have been, still the 4 that it actually were on this list, which is why I need to list them so I know which numbers I can test, because there's no point in testing 5 because there's absolutely no way that 5 could have been a 0 of this polynomial. So this means that the zeros of, let's see, what was that polynomial? I remember it had some big numbers. So the polynomial, what was it? Okay, yeah, 3x to the 5th minus 32x to the 4th plus 118x cubed minus 164x squared plus 39x plus 36 are, we said they were 1, 3, 4, and negative 1/3. And since, even though it's a fifth degree polynomial, I do know that I can say that there are only 4 zeros because 3 repeated itself. And there's no point in saying 3 is a 0 twice because 3 is a 0, 3 is a 0. That's the same statement. No point in saying the same statement twice. Yeah, 3 is a 0 either way. So you can look at that polynomial and tell that one of those 4 zeros has to be a double 0 because there should be 5 answers, but there's only 4 listed. All right, so here is a practice problem that I want you guys to try. It's not going to be too hard. This is just a third degree polynomial. So let's see. I want you guys to do, let me pull it up here. So f of x equals 2x to the third plus 9x squared minus 2x minus 24. I want you guys to, well, first I want you to list all the p and q values. Then from there, determine the possible rational zeros. And finally, I want you to actually solve what the zeros are. So since it's a third degree polynomial, that means there are three that you're looking for. So you just got to use synthetic division to figure out what they are, or figure out at least the first one, and then after that you'll be able to use a quadratic, or use the rules of quadratic to factor it. So like I said, just attempt this, and synthetic division is not hard. It's just a lot of work. So I do, like, it's just adding and multiplying and adding and multiplying and adding and multiplying repeatedly until you get zero. If you don't get zero, keep going.